This is a solution video for the Spring 2024 Exam 1 in Calculus 1 at Oklahoma State University. The first problem is a multiple choice, and so it says the expression, and it gives an expression, is the derivative of what function? Okay, and so when we are looking at this expression, we want to compare it to what we know as the definition of derivative, which is that f prime of x is equal to the limit as x goes to h, f of x plus h minus f of x all over h. And so I just want to match the different parts. So clearly this h matches that h. I can see that this limit as h goes to 0 matches with that. I can see that f of x should match with this portion of the definition. And then the x plus h, this part here, matches f of x plus h. And so when I see that, I can see, and I'm just going to check, it looks to me like f of x is equal to, it looks like f of x is going to be equal to x cubed minus natural log of x. Now let's just double check that f of x plus h matches the part we think it is. That would be x plus h cubed minus natural log of x plus h if I plug x plus h into this function. And so that does seem to match, and so I think we can be fairly confident that our f of x is equal to x cubed minus natural log x, which is answer D. The next one says, the graph of a function is given below. For which value of k do the one-sided limits exist but are not equal? Okay, so I want the limits to exist but not be equal. So that would be looking for something like a jump discontinuity. Or maybe an infinite discontinuity if one's going to positive infinity and one's going to negative infinity. I do see an infinite discontinuity here, but that one is, they're both going to infinity. So this is what we would call an infinite discontinuity. And at C, we have a discontinuity also, but this one is called removable because I could just plug that hole with a point. At part A is where we have the jump discontinuity. So the left-hand limit, as I come in towards A from the left, the y coordinates are going to one value. And as I come in from the right, as I come in from the right, the y coordinates are going to one value. As I come in from the left, the y values are going towards another y value. So at A, the left and right-hand limits exist, but are not equal. The third one says, imagine the vase is pictured below is filled with water. Let V represent the volume of water in the vase, and let H represent the height of water in the vase. Which of the following graphs could represent the function dH dV, the derivative of the function h with respect to V? So the derivative of the function h with respect to V. Okay, so in this one, volume is my independent variable. And height is my dependent variable. So dH dV would be a change in height over some change in volume. Okay, so if I think about how the height is changing for fixed changes in volume. So let's say I put in the first amount of volume. So down here, since the bottom is skinny, the first amount of volume that I put in is going to change the height quite a bit. And then the next fixed amount of volume that I put in is going to change the height, but it's still going to be a positive change in height, but it won't be as much of a positive change in height. In other words, it'll be closer to 0. So if I'm thinking about the volume and the dH dV, again, a positive change in volume will be a positive change in height, which means all of my y values, my dH dV values are going to be positive. But it's going to be a greater change at first, and then it's going to be not as much change as I go on. Here, again, a fixed amount of volume is going to still change the height in a positive way, but not as positive, not as much of a change. And then when I get to here, I should have some kind of a minimum. So I keep doing fixed changes in volume, but the amount of volume, it's going to be spread out. So the change in height is going to be not as much. I should have a minimum of my graph there. And then as I continue to add fixed amounts of volume, my height is going to be increasing at a faster and faster rate until I get here. And then whatever that rate is should be fixed changes in volume should give me the same change in height. So my dH dV will be a constant for those. So it should end up giving me graph B. Okay, so all right, so I'm wanting to compare different things like f of b minus f of a and f of b minus f of a over b minus a and so on. Okay, so, well, for this graph, I can actually find point coordinates here. So A looks like it's about 2.5, and the height there is about 1. B looks like it's about 5.5, and the height there is 3.5. So if I did f of b minus f of a, that's approximately 3.5 minus 1, which is about 2.5. Okay. If I did f of b minus f of a over b minus a, so f of b minus f of a is just this change in height here. It's this change in the y value. So that's what this is. F of b minus f of a of b minus a, that's going to be the slope of this line. So that's the slope of that green line is going to be that. So I can compute that. It's about 3.5 minus 1 over 5.5 minus 2.5, which is, I don't know, let me get a calculator. When I plug that into my calculator, I get approximately 8.833, something like that. That's the slope of that line. And then the limit as h goes to 0 of f of a plus h minus f of a over h, that would be the slope of the tangent line to the graph at a. So if I drew in a tangent line there, well, that's just actually 0. So it's the slope of that yellow line. And I can just see from the graph that that is going to be a slope 0. The slope of that yellow line is going to be 0. Okay, so now I want to put them in order. So it looks like the smallest one is this one with the limit, and then the next smallest one, so I can X out those two. The next smallest one is the slope of the secant line, and then the change in y. So the correct answer is D there. Okay, so the next one is asking basically just which one represents the derivative. Okay, and so if I look at this first one, I would say that's not the derivative because it needs to contain a limit. This one would be an approximation of the derivative, as an approximation of the derivative limit from the right-hand side because it's adding 0.00001. So this is an approximation of the derivative. This is like a slope of the secant line. This one here actually represents the definition of derivative, and so does this one. With that delta x, you may have used an h in class instead of delta x, but that's the same thing, so that one also works. Oh, actually, I saw the wrong thing. I just noticed on the third one, if you notice that this has h going to 0, but It doesn't have any h's in the limit, so that one actually is not going to work. It tricked me. Okay, but this last one here, this last one here is 1, so it has the limit as x goes to a of f of x minus f of a over x minus a. So 4 and 5 are the only ones that are right, so the correct answer is E. All right, so for this one, it says consider the function defined by this thing, okay? I want to compute the derivative, so I can use the power rule to differentiate. So the derivative with respect to x of 6 minus x squared is going to be the derivative of 6 is 0, and then I'll have minus, and the derivative of x squared is 2x, so it's equal to negative 2x. Then it says compute the derivative of mx plus b in terms of the constant m and b. So the derivative with respect to x of mx plus b is just going to be m times the derivative of x is 1 plus the derivative of b is just a constant is 0. So this is equal to m. And then it says determine the values of constants m and b that make f continuous and differentiable at x equal 2. So to be continuous means that the slope has to match and the y value has to match. So I can use my work on parts A and B to make sure that the derivative or the slope of the tangent matches on the left and right side at the x value x equal 2. So we want at x equal 2, we want negative 2x to equal the m. So I'm just going to plug negative 2, or I'm going to plug 2 in for x. So I get negative 2 times 2 should be my m. So in other words, m needs to be negative 4. So that's the first part. Now I want mx plus b. I want the y coordinate mx plus b to equal the y coordinate on the left, which is 6 minus x squared. So we want this to be true when at x equal 2. Okay, and so I've already found my value that I want for m, and that is negative 4. And I want the value x equal 2, so I'll plug in 2 for x, plus b, that's the value I'm trying to find, equals 6 minus x squared. Again, x is 2, so 2 squared. And so I can solve for b here. So I'll have negative 8 plus b is equal to 6 minus 4, so that'll be 2. And so I'll get b is equal to 2 plus 8, which is 10. So mx plus b needs to equal, the m is negative 4x plus 10. So that's our answer. Okay. Next, it says I have this Shockley equation given by that, where I represents the diode current, and I sub S represents the reverse saturation current. Okay. So describe the following expressions, specify the units. Okay, so one thing you want to look at is what are my independent and dependent variables here. So this part right here is a big clue. It's telling me that the independent variable is V. So V, which is the voltage, so is the independent variable. So I'll just write the independent variable is V, which is voltage. And the dependent variable is equal to I, and I stands for the diode current. Okay, and so if I did f of 0.71 minus f of 0.65, I know that these inputs here are volumes, are voltage. So I can say this is going to be the difference in the current as the voltage increases from 0.65, what's for voltage? Volts to 0.71 volts. Okay, so that's just telling me the difference in current. Now here I have the difference in current over the difference in volts. And so this is going to be the average rate of change in volts per, so it's in, the I is the current. So it's going to be, current is measured in what now? Microamps per volt on the interval 0.65 volts to 0.71 volts. Okay, and now this one is the instantaneous rate of change in microamps per volt at V equals 0.65 volts. Okay, and then what does the solution to the equation f prime of V equals 0.013 represent? So that would be, so this is a volt and this is a rate of change. So that would be, so the solution is the voltage at which the rate of change, instantaneous rate of change and current is 0.013 microamps per volt. Okay, so that 0.013 is a value of the derivative, so that is a rate of change, and I want to find what voltage has that rate of change. Okay, so for this one, we're just going to fill in here. So this distance from A to A plus H, that distance is going to be H. So I start at A, I go over H, I get A plus H. The function evaluated at A is this f of A. The function evaluated at A plus H is this f of A plus H. That means this is f of A plus H minus f of A will be that change in the y. And so the slope between these two is equal to f of A plus H minus f of A over H. And then this slope is equal to the limit as H goes to 0 of f of A plus H minus f of A all over H, which is also equal to f prime at A. So for these, I'm looking at these limits. So the limit as x approaches -3 from the right. So as I'm coming in towards -3 from the right, my y value is going to the y value 2. F prime at -4. So if I go over here to -4, I can see that it is linear there. So I just want to compute the rise over run. So if I scooch over to the right one, I go up 4. So the slope there is the rise is 4 and the run is 1. So 4 over 1. So that makes 4 for the slope of this line right here, line segment. The limit as x approaches 2 from the right. So as I'm approaching the y value or the x value 2 from the right hand side, I can see this is going off to infinity. So I can say that's going off to infinity. So technically that limit doesn't exist, but it doesn't exist in the sense that it's going off to infinity, it increases without bound. Okay, this here I can see is the definition of derivative at the value -3.7. So if I go over to -3.7 on my x-axis, that would be somewhere around here, which would be this line here. So I want to do the instantaneous rate of change at that time, so I'm looking for this slope, which we've already decided is 4. This is the limit as x approaches 3 of f of x, and so if I look, my left and right hand limits are approaching the same y value, and the y value there is 0. Even though there's a hole there, the limit still exists because the left and right hand limits are approaching the same y value. The y value is 0. This is asking for the derivative of f when x equals -1. And so if I go over here to -1 on my graph, I can see that the slope from the right and left are actually approaching different, there are different slopes on the right and left. I have a cusp or a corner there at x equal -1, so that means the derivative does not exist there because the left and right hand slopes are not matching up. They're different slopes. Okay, the next one is the limit as x goes to 1 of f of x minus f of 1 over x minus 1. So this would represent the derivative of the function f of x at x equal 1. So if I go over here to where 1 is on my graph, I can see that the derivative there is 0. That is a horizontal line with slope 0. So the slope of the tangent is 0 there. The derivative is 0 at x equal 1. The next one is looking at the limit as x approaches -3 from the left. So as x approaches -3 from the left, my y values are going up to the y value 4. So that's equal to 4. And then this is the limit as x approaches -1, and this is a two-sided limit. So as x approaches -1, so from the left and the right, both the left and right are approaching the y value 2. So the correct answer there is 2. Okay, for this one, I want to evaluate some limits. And so here I'm going to do some evaluation here of these. So I can see here that I notice that if I plug in 1, I get e to the first minus e. On the bottom is going to 0. So I'm probably going to need to do some kind of a algebraic thing here to get rid of that e to the x minus e. I look at the top and I notice that there is a factor of x squared in both terms on the top. So I can write this as the limit as x goes to 1. I can factor out the x squared from both of those. I'll get e to the x minus e here over e to the x minus e. So I have e to the x minus e over e to the x minus e. That divides to make 1. So I'm just left with the limit as x goes to 1 of x squared, which is equal to 1. So your answer there is 1. For this one, I'm looking for the limit as x approaches k from the left. Okay, and so I'm looking at some value k, and as I'm approaching k from the left-hand side, that means I'm plugging in values that are smaller than k. So if I think about that, that's telling me that if I'm plugging in values that are smaller than k, that means that x minus k will be negative because I'm plugging in x values that are smaller than k. And that means that the absolute value of x minus k will be positive when I take the absolute value of this. So that's going to give me a positive number divided by a negative number, and they actually have the same value, but just one's positive and one's negative. So this is going to actually equal -1 there. Because I have the same x minus k on top and bottom, except one is negative and one is positive. So when you divide that out, you're just going to get -1 there. Okay, then I want to use the definition of derivative to show this derivative. And so I want to take the limit as h goes to 0 of f of x plus h minus f of x over h. And so now I'm going to plug in. So I'm going to continue to write my limit until I take the limit. So I'm going to plug in that into my function f. So x plus h squared minus 5 times x plus h minus the function f of x, 3x squared minus 5x over h. So I'm just going to go ahead and do some algebra to reduce this down. So that's going to be 3 times, when I square that, the x plus h times x plus h, I multiply that all out, I'll get x squared plus 2xh plus h squared, minus 5x minus 5h. And then I'm going to distribute this minus sign, minus 3x squared plus 5x, all over h. Continue to write the limit until we take the limit. We haven't taken the limit yet. Now I'm going to distribute that 3 in there. 3x squared plus 6xh plus 3h squared minus 5x minus 5h minus 3x squared plus 5x, all over h. Now I can get rid of everything that adds to 0. So 3x squared minus 3x squared adds to 0. Negative 5x plus 5x. Everything else is going to have an h in it. So I have the limit as h goes to 0 of, let's see, I think what's left is 3h squared plus 6xh minus 5h, all over h. Now I can factor out an h from the top. So I'll have 3h plus 6x minus 5, all over h. Now h divided by h, that divides to make 1. So what we're left with is the limit as h goes to 0 of 3h plus 6x minus 5. Now I'm at the point where I can take that limit because I don't have that h going to 0 in the denominator anymore. So now I can go ahead and plug in 0 for h, and that gives me 3 times 0 plus 6x minus 5, which reduces to 6x minus 5, which is what I was going for. So we're done there.